black color flat plate which is made up of bakelite. At the bottom of this black color bakelite plate, there is a small hole. And here, the other thing what we have here is, here there is a water tank. In the water tank, we have water and there is a immersion type of heater is placed in the water tank. And as for the other part of this experiment here this is a temperature indicator switch which is used to read the temperatures measured by the thermocouples which are connected on the surface of the copper hemisphere as well as on the a test disk as shown here. There are four thermocouples. Three are connected on the outside surface of copper hemisphere and the other one is connected to measure the surface of this temperature, this circular disk which is positioned uh, in an sleeve which is made up of a bakelite insulating sleeve. And here, with the help of this particular switch, we can control the to what temperature the water in the tank can be heated. For example, if we set the temperature to, let us say, some 90 degrees Celsius, once the temperature of the water in the tank reaches 90 degrees Celsius, then the power input to the heater, the immersion heater is switched off. And here this water tank is connected to the dome through this pipe. And here there are two valves. One valve is here and the other one valve is here. This valve is used to evacuate the water in between the white colored dome as well as in between the copper hemisphere. As per the selection of the copper hemisphere, so it is purely selected because the evacuation of the water which is stored in between these two spaces will become easier if we select the hemispherical shape. And this is the temperature indicator switch. By pressing these switches, we can read the temperatures measured by the four thermocouples. Three thermocouples are mounted on the surface of the upper hemisphere, and the fourth thermocouple is connected to measure the surface temperature of the small circular disk. This is regarding the details about this particular experimental setup. As for the experimental procedure, the first thing that we do is that we select some temperature for the water temperature to which the water in the tank to be heated. For example, we'll select some 70 degrees Celsius. So we set that 70 degrees Celsius temperature here, we switch on the power supply, then the immersion heater is energized and the water in the tank is heated to the 70 degrees Celsius. Then we open this valve completely and slowly we open this valve to partially so that if at all there is any water that is remaining between copper hemisphere and the dome to completely drain out. Then we close this valve and we open this valve completely so that the hot water at a desired temperature is filled between the copper hemisphere and the outer dome. As the hemisphere is made up of copper, which has high thermal conductivity. So after some time, you can assume that the entire surface temperature of the copper hemisphere is more or less at the same temperature, and the system reaches the steady state temperature. That means we can say that the entire surface temperature of the copper is more or less at the same temperature, which we can measure it using the thermocouples that are connected to the surface of the copper hemisphere, which we can read it from this multi-temperature indicator switch. The amount of water is filled in such a way that its heat capacity is large enough that the surface temperature of the copper dome does not decrease in a short span of time. Then what we do is that we blacken this circular disc, which is positioned in a sleeve which is made up of bakelite. We'll place this particular circular disc in the hole which is located on the black plate. Yeah, here you can see that at the bottom of this flat plate, there is a hole here. On top of the hole, this copper hemisphere is placed. And now, once the system, the copper hemisphere temperature is at more or less constant, then we place this small circular disc, which is blackened, in the hole. And then we note down the temperatures of this surface temperature of this particular disk, which is positioned in the circular hole. First, we note down the surface temperature of the small circular disk, which is positioned in this test region. That particular temperature at which we position inside is noted down, which is taken as the temperature of this particular disk at T is equal to 0. Here, small t is the time. So the after we place this circular disc inside the hole, the copper hemisphere is at higher temperature, and this circular disc is more or less at the atmospheric temperature, which we can read it from the multi-temperature table. There is a temperature difference between the copper hemisphere and this small circular disc. Heat transfer takes place from the copper hemisphere surface to the small circular disc by radiation. Here we want to find out the heat transfer rate from the copper hemisphere to the small circular disc by radiation. We only intend to calculate that quantity only, so that we want to find out the Stephen Boltzmann constant experimentally, and to verify whether the experimentally calculated value is in agreement with the theoretically obtained value. The that is the experimental procedure. After placing the small circular disc in the test region, we will note down the temperatures of the surface of the small circular disc for every 5 seconds. That is concerning the experimental procedure. To say about a little bit of theory, Stephen Boltzmann law says that the emissive power from a black body is directly proportional to the fourth power of the absolute temperature of the surface. Here, the proportionality constant is the Stephen Boltzmann constant, which is equal to 5.67 into 10 power minus 8 watt per meter square Kelvin to the power of 4. So, we want to find out this Stephen Boltzmann constant from this particular experiment, and to see if at all there is any difference between the experimentally obtained value and the theoretical, the calculated value. As for the calculations that needs to be performed in this experiment, that is concerning the experimental procedure. So these are the dimensions of the test disk, which is enclosed in a sleeve. So this diameter of the small disk that I was talking about is having a diameter of 20.4 mm, and we also know the mass of this brass disk, that is 5.05 grams. And as I was saying, there are four thermocouples are being used. Three are connected on the outside surface of the copper hemisphere, and the fourth one is connected to measure the surface temperature of the test disk. So this is the Stephen Boltzmann law that I was talking about. Here we want to find out this Stephen Boltzmann constant sigma from the experiment, and to verify whether this value is an theoretical value or not. we have already looked into the experimental procedure. So a given quantity of water, which is in the tank, is heated using a immersion heater to a set temperature. In this particular case, you can take it as 90 to 95 degrees, anywhere in between those. Then the hot water, which is available at the set temperature, is allowed to enter the water jacket that is surrounding the copper hemisphere and the outer dome. When the three thermocouples that are mounted on the outside surface of the copper dome show a steady state temperature reading, then we insert the small disk in the test region. At the time of insertion of the test of the disk in the small hole, the temperature of the disk is also noted. That temperature is taken as at the T is equal to 0. A small t is equal to 0. Then for every 5 seconds, we note down the change in surface temperature of the small test disk. So we'll note down about 20 readings at for every 5 seconds. We'll note down the surface temperature of the test disks for every 5 seconds. As per the calculation procedure, we want to find out the average surface temperature of the copper hemisphere. So we are obtaining the surface temperature of the copper hemisphere at three locations. We simply average those three readings and say that that would be the average surface temperature of the copper hemisphere. And we'll convert that into kelvins, and we'll also note down the temperature of the disk at the instant when it is inserted. So as I have mentioned, at small t is equal to 0, we note down the surface temperature of the disk, which is called as the T4 is equal to some value, more or less it will be the atmospheric temperature. We'll again convert it to in terms of the Kelvin. As for the readings, we'll only note down the for every 5 seconds how the temperature of the surface temperature of the test disk is changing. This is the only observation that we are going to make in the experiment. As for the theoretical procedure, radiation heat transfer from the circular spherical copper hemisphere to the test disk Q is equal to sigma A T to the power of 4 minus T4 to the power of 4. So this is the more or less will be is equal to the temperature of this surface temperature of the test disk at time t is equal to 0. T is the average surface temperature of the copper disk. So this gives us the amount of heat transferred from the copper hemisphere to the test, test disk by radiation, which is equal to the change in internal energy of the test disk, which is equal to mcp d t by capital T by d small t at t is equal to 0. Here notice that we are taking this slope change in temperature with respect to time at t is equal to 0. This term only talks about the heat transfer by radiation only. So we want to ensure that the heat transfer by other modes, that could be heat transfer by radiation from the flat plate to the test disk, we do not want to incorporate that component in the calculation part when we are calculating the change in internal energy. Because of that one, we want to calculate the slope of the change in temperature with respect to time at t is equal to 0. So we plot, you note down the temperature with respect to time at every 5 seconds, then you plot the temperature that is T4 versus T, then you fit a curve and you draw a tangent at T is equal to uh, 0, then we find out the slope. We know the mass of the test disk and we know the specific heat of the brass material, and we have found out dt by d capital T by d small t at t is equal to 0 from curve fitting, and we already know the diameter of the disk. We can find out its area, and we already found out the average brass hemisphere surface temperature, and we already know the surface temperature of the test disk at T is equal to 0. Once we substitute all these quantities here, we can find out the Stephen Boltzmann constant from experiments. Then you can see what would be the error in the obtained value, and you can discuss what could be the possible reasons for that discrepancy between the experiments and theory. Yeah, that's all for this particular experiment. So you can go through the theory, and you'll also come across the theory in the heat transfer course, and also you can read this manual as well as you can go through the video again just to familiarize yourself with this, how this experiment is being conducted, and also a little bit of details concerning the experimental procedure as well as some precautions. Okay, that's all for today as per the explanation. So you can write the report for this particular experiment by next week. So now I will call out the absentees, and if there are Vishnu, are you there?
Yes, sir.
Yeah, I'll just call out the absentees. Just check with you what you have. Okay.
Yes, sir. I
10.
already noted the students' roll number, sir.
Yeah, well, let's see if at all anyone added in the last one. Okay. Just I'll call
Okay.
out. Okay, 10, 11,
Okay, sir. I will
18.
call them. Hello, sir.
Yeah, yeah.
Shall I call them the
No, no,
absentees?
I'm calling out. You just check what you have. Okay.
Okay, okay, sir.
Uh, 10, 11,
Yes, sir.
18, okay,
Okay. 15,
20.
15 absent in my
No,
thing.
no, 15 is here. Okay.
Okay.
21, 22.
Sir, 22 having power cut issues sir, in their area, so he was unable to attend.
Okay. You can
Okay.
take out the 22 also. Okay. 28,
Yes, sir.
41,
Yes, sir.
44.
43, I put.
Yeah, is here.
Okay, sir.
52, 57,
Okay.
63,
Okay.
68, 69.
Yes, sir. 78. No.
I see is here. 86 and 89. I don't know. Is there anyone beyond 88?
88, sir. Mine.
Yeah, yeah. 88, you are here. Fine.
Yes.
Okay. That's all.
Yes, sir. I noted down. It's okay.
Sir,
Okay,
and
fine.
78 is also present, sir.
Yeah, 78 I put to present.
No,
Okay.
you're fine. Okay. Okay, guys,
Sir,
that's all. So you can write down the report for this particular experiment by next week. Okay. We'll discuss about the last experiment, that is the demonstration of the performance of heat pipe in the next week.
Okay, sir.
sir, what about actually we have to give only 2 days, no, sir, for this.
No, no, no. For this one,
Previously 2 experiments we have conducted, no,
yeah,
sir.
yeah. Okay. See, in the last class, probably you have covered 2 experiments. The second report, they can submit it by the end of this Sunday. Okay.
Sunday I will put. Okay, sir.
Okay.
Sir,
Okay,
one
sir.
experiment is we have to submit on 5th, sir. Can you extend it, sir?
Yeah,
Already we have.
that's what sir is saying, no.
Sunday,
Sunday.
6.
Okay. Yeah, sir. Okay. Fine.
Okay.
Sunday midnight I will put.
Thank
Okay.
you.
Okay.
Till Sunday midnight I will put.
Yeah, yeah, fine. That should be okay.
Okay.
Okay, guys. We'll again meet in the next class.
Thank you.
Thank you.
Okay.